So in the last lesson, we tied together what we've learned about the first and second derivative with some other things like finding asymptotes, symmetry, and intercepts. This first problem is just kind of a review of that. So hopefully you guys have already attempted it. I'm going to start with the asymptotes, specifically the vertical asymptotes. We know that the vertical asymptotes occur where our denominator is 0, where our function is undefined. Our denominator is x squared plus 4. So if we solved that, we have x squared plus 4 equals 0. We'd have x squared equals -4. And again, we can't have a negative number if we are squaring a value. So therefore, there are no vertical asymptotes. To find the horizontal asymptotes, since it's not as clear as what is the highest degree of the numerator and denominator, we're going to go back to using limits. First, I want to know what the limit as x approaches positive infinity of 3x divided by the square root of x squared plus 4. I'm going to divide everything by the highest degree of the denominator, which is the square root of x squared. So I have the limit as x approaches infinity, the square root of x squared plus 4 divided by the square root of x squared over 3x divided by the square root of x squared. And yesterday we said that the square root of x squared is the same thing as the absolute value of x. And if the values of x are greater than 0, which they would be where x is approaching infinity, then we know that the absolute value of x is just going to be x. So I have the limit as x approaches infinity of 3x divided by x would be 3 over the square root of x squared divided by x squared is 1 plus 4 divided by x squared. As x increases without bound, our denominator is getting really big, so overall this piece is going to be approaching 0. So I have 3 over the square root of 1, which would be 3. Now we need to check the other end. We're going to look at the limit as x is approaching negative infinity of 3x divided by the square root of x squared plus 4. And again, I'm going to divide everything by the highest degree of the denominator, the square root of x squared. So I have the limit as x approaches negative infinity. On the bottom, I have x squared plus 4 divided by square root of x squared. On top, I have 3x divided by the square root of x squared. And again, we said that's the absolute value of x, and the absolute value of x is going to be negative x if we're talking about x values that are less than 0. And if we're approaching negative infinity, we're definitely looking at x values that are less than 0. So that would be negative x. So I have the limit as x is approaching negative infinity of 3x divided by negative x, or -3, over the square root of x squared divided by x squared would be 1, plus 4 divided by x squared. As x approaches negative infinity, this piece is going to approach 0. So we have -3 over the square root of 1 plus 0, which would be -3. So we have horizontal asymptotes at y equals positive and -3. On the right side, we'll be approaching +3. On the left side, we'd be approaching -3. So that takes care of our horizontal and our vertical asymptotes. Next, we want to know what kind of symmetry the graph has. So for symmetry, I'm going to go back to plugging in -x into the function. So symmetry. We already know that we're dealing with the function, so we know it doesn't have x-axis symmetry because that would make it not a function. What we want to know is, does it have y-axis symmetry or origin symmetry. Both of those we can determine by looking at f of negative x. If we plug in f of negative x, then we get positive f of x. It has y-axis symmetry. And if we get negative f of x, it has origin symmetry. If we don't get either of those things, then it doesn't have either type of symmetry. So I have 3 times negative x divided by the square root of negative x squared plus 4, which would give me negative 3x divided by the square root of negative x squared is x squared plus 4. I started with 3x over the square root of x squared plus 4. I ended up with negative 3x over the square root of x4. In other words, I ended up with negative f of x. Therefore, we can conclude that f has origin symmetry. And last, we're going to find our intercepts. We're going to look for the x and the y-intercept. We'll start with the x-intercept, which is where our function value is equal to 0. Well, the only way that this could be equal to 0 is if its numerator is equal to 0, and that happens if x is 0. To find the y-intercept, we're looking for our y value or our function value when x is 0. So we'd have 3 times 0 is 0 divided by the square root of 4 is 2, which gives us 0. So again, here, both the x and y-intercept are the same point at the origin. In part 2, we're going to sketch a graph that's continuous and has the following characteristics. So it has to be a function and it has to be continuous. Those are things to keep in mind also in addition to the things that they've listed out. So we need to make sure that we don't have any holes, any jumps, any vertical asymptotes. We also want to make sure that our function doesn't have more than one output for each input. In other words, it would pass the vertical line test. So the first thing they've told us is the domain is negative infinity to positive infinity. So then we know that it's continuous for all values of x. Part B tells us that f of negative x is equal to f of x. So in other words, whether I plug in the negative x value or the positive x value, here or here, I'm going to get the same function value. In other words, they're telling us that this has y-axis symmetry. Which is important because if I can figure out what half of the graph looks like, I'll immediately know what the other half on the other side of the y-axis is going to look like as well. They tell us that f of 0 equals f of 2, which is 0. Okay, so we can go ahead and plot those points. F of 0 is 0, so here. F of 2 is also 0, here. And if we want to, we can go ahead and tie that in with what we know from part B. This has y-axis symmetry. If f of 2 is 0, then f of negative 2 is also 0. So this point would also be a point on our graph. D tells us that f of 1 is 3. So we have the point 1, 3. And again, if f of 1 is 3, then f of negative 1 must also be 3 because of that y-axis symmetry. The derivative at 0 does not exist. Well, we know there's a few things that would cause the derivative to not exist. One of them is discontinuity, but we know it's not discontinuity because it has to be continuous. So then that means that there's two other options. Either we have a vertical tangent line, which is probably not going to be likely, but maybe, or we have a sharp point. So this tells us we have a vertical tangent line or possibly a sharp point. So we might have to come back to that idea. F tells us that f prime is less than 0 from 1 to infinity, and f prime is greater than 0 from 0 to 1. So f prime is less than 0. In other words, the derivative is negative from 1 to infinity. So from 1 to infinity, since the derivative is negative, we know that we are decreasing. From 0 to 1, we know that the derivative is greater than 0, is positive, so it's increasing. In part G, they tell us that the second derivative is less than 0 from 0 to 2. So from 0 to 2, our second derivative is negative, so we're concave down. And from 2 to infinity, our second derivative is positive, so we're concave up. And then last but not least, they tell us that as x approaches infinity, f of x approaches negative 1. In other words, we have a horizontal asymptote at y equals negative 1. And because this has y-axis symmetry, whatever the right side of my graph is doing, the left side has to be the reflection of that. So if the right side of my graph is approaching a value of 1 as x increases without bound, then the left side of my graph must also be approaching that same value as x decreases without bound. So let's see if we could draw all this together. We know that from 0 to 2, the graph is concave down. It's increasing from 0 to 1 and decreasing thereafter. So our graph is increasing and concave down, then it's decreasing and concave down. After 2, it's still decreasing, but then it starts to become concave up and must approach that value of negative 1. If we know what this side of our graph looks like, then we can go ahead and reflect that across the y-axis. So here, my graph must look something like that. Notice at 0, we have a sharp point, which also verifies that condition E, that the derivative does not exist at 0. So we have a graph that has a sharp point at 0, it's not differentiable. So just to double check, domain is all real numbers, that works. F of 0 and f of 2 are 0. F of 1 is 3. We have our y-axis symmetry. I think I skipped that part. If I reflect the right over the graph, over the y-axis, I get the left part of my graph. The derivative does not exist at 0 because of a sharp point. The derivative is negative from 1 to infinity, so the graph is decreasing from 1 to infinity. Got it. And positive from 0 to 1, increasing from 0 to 1. Got that. The second derivative is negative from 0 to 2, so concave down from 0 to 2. And then positive from 2 to infinity, so concave up from 2 to infinity. And our graph is approaching negative 1 as our x values increase without bound. So it meets all of our conditions.